Hello friends, in this lecture we discuss how can we find the complete solution of the nth order linear differential equation with constant coefficient. Here suppose that dny by dxn plus dn minus 1 y by dxn minus 1 plus dn minus 2 y by dxn minus 2 and so on. Here this is suppose p naught, here p1 and here pn y is equal to q. This is you know that this is linear differential equation with constant coefficient. Linear differential equation with constant coefficients. Constant coefficients. Here we find the complete solution of this nth order linear differential equation with constant coefficient. Already you see in the previous lecture, when q is equal to 0, how can find the solution of the nth order linear differential equation. There are three cases in the previous lecture. If the root of the auxiliary equation are distinct, if the some roots of the auxiliary equation are equal, and the third case is if some roots are imaginary. Now we find the solution, complete solution of this nth order linear differential equation with constant coefficient when q not equal to 0. When q not equal to 0. You know that complete solution of one is complete solution of one have two parts. Y is equal to fx plus phi x. Y is equal to fx plus phi x be the complete solution of 1. Be the complete solution of 1. Here fx is called the complementary function. Complementary function, and phi x is called the particular integral. You know that this equation 1 is nth order linear differential equation with constant coefficient. The given differential equation is nth order linear differential equation with constant coefficient. Here q not equal to 0. Then the complete solution of 1 have two parts. Y is equal to fx plus phi x. Here fx is called the complementary function and phi x is called the particular integral. So this can be also written as, so this second can be also written as y is equal to cf plus pi. Cf is the complementary function and pi is the particular integral. Now we see how can we find the particular integral of this linear differential equation. You know CF is the solution of equation f dy is equal to 0, where this equation 1 can be written as f dy is equal to q. So CF is the complementary function and complementary function is the solution of this equation where q is equal to 0. Now we find the particular integral on the right hand side. So particular integral, how can we find particular integral if q is equal to e to the power s? To find the particular integral if q is equal to e to the power ax, where f a not equal to 0. Now we find the particular integral if q is of the form e to the power ax, where fa not equal to 0 and a is some constant. A is some constant. Now we see here this is nth order linear differential equation with constant coefficient. This can be written as also written as f dy is equal to q. This is called linear differential equation with constant coefficient. When q not equal to 0, the complete solution of 1 have two parts. You know that the complete solution of 1 have two parts, y equal to fx plus phi x. Fx is called the complementary function and phi x is called the particular integral. This can be also written as y is equal to complementary function plus particular integral. You know that complementary function is the solution of the equation f dy is equal to 0. If q is equal to 0, then cf is the complementary function of this equation, and cf is the solution of this equation f dy is equal to 0. Now we find the particular integral if q is equal to e to the power ax, where a is some constant and fa not equal to 0. Now you can see, let us suppose that if we differentiate e to the power ax one time, here capital D means d by dx. Now we differentiate e to the power ax one time with respect to x, we get a e to the power ax. Now we again differentiate this, so find second derivative of e to the power ax with respect to x, we get a is the constant, and again we differentiate e to the power ax, we get a e to the power ax, so it becomes a square e to the power ax. Now again we differentiate with respect to x, that means here we find third order derivative of e to the power ax with respect to x, we get a cube e to the power ax. So you can see here, when we differentiate e to the power ax one time, we get a to the power 1 e to the power ax. When we differentiate two times, we get a square. When we differentiate three times, we get a cube. So similarly, when we differentiate e to the power ax n times, we get a to the power an e to the power ax. If you can see that if fd is equal to d to the power n, then fa is equal to a to the power n. You can see that if we suppose that d to the power n, this is the nth derivative, this can be written as fd, and if we replace d by a, we get fa is equal to a to the power n. So above equation can be written as fd e to the power ax is equal to fa e to the power ax. Now fd is the function of differential operator. Now we multiply both sides 1 upon fd. 1 upon fd. Here both sides we apply 1 upon fd. fd is the function of differential operator, and 1 upon fd. 1 upon fd, this means integral. So integral, and this is the differential operator and this is the integral operator. So this will be cancelled out. So there will be e to the power ax. And fa is constant because a is constant, so it will be outside 1 upon fd integral operator. So this is fa 1 upon fd times e to the power ax. This can be also written as 1 upon fa times e to the power ax is equal to 1 upon fd times e to the power ax. So this can be also written as 1 upon fd times e to the power ax is equal to 1 upon fa e to the power ax. Here fa not equal to 0. So this is the particular integral of e to the power ax. When we find the particular integral of e to the power ax, we put in place of d, we put d is equal to a. In place of d, you can see here, we put the coefficient of x in power of e to the power x. Here a is the coefficient of x in power of e to the power ax. So in place of d we put here a. So when we find the particular integral of e to the power ax, always we put a in place of d, and a is the coefficient of x in power of e to the power ax. Now we take some example. In this example you can see here, this is the second order linear differential equation with the constant coefficient. Here 2 and 5 are constant, so this is the second order linear differential equation. This is the second order linear differential equation. This is second order linear differential equation with constant coefficient. You can see here, this is the second order linear differential equation with constant coefficient. Now we can see how can we solve this. So you can see here, d by dx, this is equal to capital D, and d2 by dx2, this is equal to d square. So here the above equation can be written as d2y plus this can be written as dy plus pi y is equal to e to the power minus x. Now taking common y, so we get d square plus 2d plus 5y is equal to e to the power minus x. This is the second order linear differential equation with constant coefficient. And we know that the complete solution of this equation 1 can have two parts. One is the complementary function and other is the particular integral. So first we find the complementary function. So for finding complementary function, you can see this is fd. You can see this part is known as fd. So first we find here auxiliary equation. So for finding auxiliary equation, we put m in place of capital D in fd. fd in place of capital D, we put here small m and get the auxiliary equation. So m square plus 2m plus 5 is equal to 0. This is the auxiliary equation. Now we can see the find this is the quadratic equation. So use here Sridharacharya formula and get the roots of this quadratic equation. So m is equal to minus 2 plus minus 4 minus 20 upon 2. So this is minus 2 plus minus 16 upon 2. So this is minus 2 plus minus 4i upon 2. So m is equal to minus 1 plus minus 2i. So you can see that these roots are imaginary, and this can be written as alpha plus minus I beta. So alpha is here minus 1 and beta is here 2. So first we write the complementary function of equation 1. So the complementary function can be written as e to the power alpha x c1 cos beta x plus c2 sin beta x. Now we put value of alpha and beta and get the solution and get the complementary function of given second order linear differential equation with constant coefficient. You can see here alpha is equal to minus 1 and beta is equal to 2. So we put value of alpha and beta and get the complementary function. So this is e to the power minus x c1 cos 2x plus c2 sin 2. So you can see here, first we write d2y by dx2 as capital D square y and dy by dx as capital Dy plus 5y and taking common y. We know that this is equal to capital Fd. Now we find the auxiliary equation. For finding auxiliary equation, replace capital D as small m. Replace m in place of capital D. So we get auxiliary equation m square plus 2m plus 5. equal to 0. This is the quadratic equation. So we using here Sridharacharya formula and get the roots of this quadratic equation. Roots are -1 plus -2i. These roots are imaginary. So compared with alpha plus minus I beta, we get real part, that is alpha is equal to -1 and imaginary part beta is equal to 2 here. And we know that the complementary function, if the roots are imaginary, can be written as e to the power alpha x c1 cos beta x plus c2 sin beta x. Now we put value of alpha and beta, get the complementary function of the equation 1. Now we find the particular integral. You know that particular integral can be written as 1 upon fd times e to the power ax. Here e to the power ax is e to the power minus x. You can see here a is equal to -1 because we know that particular integral of e to the power ax can be written as 1 upon fa e to the power ax, where fa not equal to 0. So using this formula, you can see here replace d by a. So here fd is the given second order linear differential equation with constant coefficient. This is d square plus 2d plus 5 and e to the power minus x. So put -1 in place of d, we get the particular integral. So this is -1 square plus 2 times -1 plus 5 e to the power minus x. So -1 square, this is +1 plus -2 plus 5 e to the power -1. If 5 plus 1 6 -2, this is 4 and e to the power minus x. So this is the particular integral. Now we find y is equal to cf plus pi. So y is equal to e to the power minus x, c1 cos 2x plus c2 sin 2x and plus 1 upon 4 e to the power minus x. This is the complete solution of the given second order linear differential equation with constant coefficient. This is the complete solution of the second order linear differential equation with constant coefficients. So you can see here, if we find the complete solution, we find two parts. One is the complementary function and other is the particular integral. So particular integral of e to the power ax can be obtained when replace d by a. Now we take another example, second. Now we take second example. Here you can see that this is d square minus 2d plus 1y is equal to 2e to the power 5x by 2. This can be also written as f dy is equal to 2 times e to the power 5x by 2. Here fd is equal to, you can see that here capital FD, this is equal to d square minus 2d plus 1. This is the differential operator. Now first we find, you can see here, this is the second order linear differential equation with constant coefficient. This is the second order linear differential equation with constant coefficient. This is the second order linear differential equation with constant coefficient. You know that solution of the linear differential equation with constant coefficient can have two parts. One is the complementary function and the second is the particular integral. So first we find the complementary function. For finding the complementary function, first we find auxiliary equation. Auxiliary equation can be obtained from fd. So in place of d we replace m. So m square minus 2m plus 1 and equal to 0. Now we can see here, this can be written as m minus 1 whole square. So the roots of this quadratic equation is 1, 1. So the complementary function is c1x plus c2 e to the power 1x. You know that if the roots of the auxiliary equation are equal, then the solution can be written as c1x plus c2 times e to the power m1x, and m1 is 1 here, so this can be written as c1x plus c2 times e to the power x. Now we find the particular integral. So for finding particular integral, we write here 1 upon fd and e to the power x. 1 upon fd, you can see here this is d square minus 2d plus 1, and in place of e to the power x you can see here 2 e to the power 5x upon 2. This 2 is constant, so it will be outside the operator, d square minus 2d plus 1 and e to the power 5x upon 2. You know that if we find the particular integral of e to the power ax, this will be 1 upon fa times e to the power ax, where fa not equal to 0. You can see here, if we find the particular integral of e to the power ax, we replace a, small a, in place of capital D, and we see fa not equal to 0. So in place of a, you can see here this is 5 by 2. So replace this d by 5 by 2. So this can be written as 1 upon d minus 1 whole square e to the power 5x by 2, and we replace this d by 5 by 2. So we get here 5 by 2 minus 1 whole square e to the power 5x by 2. 5 by 2 minus 1, this is 3 by 2. So this can be written as 2 times 1 upon 3 by 2 whole square e to the power 5x upon 2. This is 9 by 4. So 2 multiplied by 1 upon 9 by 4 times e to the power 5x upon 2. 4 to 8 by 9 e to the power 5x upon 2. So this is the particular integral of the given linear differential equation with constant coefficient. Now we find complementary function and particular integral. If we add these complementary function and particular integral, we get the complete solution of the given second order linear differential equation with constant coefficient. Now the solution can be written as y is equal to cf plus pi, complementary function plus particular integral. So the complementary function is c1x plus c2 times e to the power x plus 8 by 9 times e to the power 5x divided by 2. So this is the complete solution of the given second order linear differential equation. This is the complete solution of second order linear differential equation is y equal to c1x plus c2 times e to the power x plus 8 by 9 times e to the power 5x by 2. So when we find the complete solution of the linear differential equation with constant coefficient, first we find the complementary function and then we find the particular integral, and when we add complementary function and particular integral, we get the complete solution of linear differential equation with constant coefficient. Thank you.